let's hop on into this one. This one's pretty simple. Well, it doesn't have any voltage sources, and so that would probably mess up a lot of students. But honestly, it's really not that big a deal. So this is drawn to trip you up. It's drawn to trip you up, but honestly, don't let it. So I'm going to redraw it just so that you can see how I see this. And I see it very simply. All I'm going to do is straighten out some of these resistors. So instead of this resistor being diagonal, I'm just going to put it vertical. Boom, boom, boom. And that was 2. And I'm going to stretch this guy out. We're still going to call this node A right here. And then I'm going to drop the 4 here. And so that's
going to add the ground.
Yep. And as long as it's hitting the ground, as long as everything are between the same exact 2 nodes, everything's good. So the source is touching A. It's good to go. This resistor is touching A. This resistor is touching A. And all 3 of those guys are still touching the ground. It's still valid. I'm going to stretch this over, drop my 2, then put my 8, then put my 8, and then put my 4. And this will be BB, right? Well, that'll be B, and bam, I've redrawn the circuit. You don't have to do this if you don't feel a need to, but for a lot of students who will see like a lot of the diagonals, it'll trip them up. And so I'm a big fan of redrawing circuits so that they look a little bit easier.
Yeah, that first 8 and that 2 is kind of confusing me a little bit, like how it's connected.
What you mean, this right here?
Yeah.
Okay, no problem.
I mean, I think I get it.
So it's like this. As long as everybody's connected to the same exact 2 nodes, you're good to go. So the 2 in this is connected to VB and it's connected to VA, right? So this 2 is connected to VA and VB. So it's good to go. You see it? So it's in the right spot. It doesn't matter how you draw it. As long as it's between the same exact 2 nodes, it's good. This 8 is touching VB and it's also touching the ground. This guy is touching VB and it's touching the ground. So you're good. So basically all I did was take the diagonals and make them straight. Cool. All right, so we just want the equations for VA and VB. It doesn't really matter which one you use. You know, normally we'd start this off by doing the voltage sources. So we'd label, well, actually, let me label some currents. So I'm going to label the currents on my diagram. I'm going to assume this. I like to assume that my currents go toward the ground. Oh, okay. I like to assume that my currents go toward the ground. So I'm going to do them like that. And then I'll assume that this 4 amp overpowers the 2. So I have the current going through the 2 to the left. So that's all. You don't have to draw it this way. You could draw however you want. As long as you draw them and stay consistent, your answer is going to be the same. All right, cool. So we have the currents drawn. So 1, you label your ground, and your currents, and your voltages. And then step 2, you do your voltage sources. The good thing is there are no voltage sources in this. And so step 3, you automatically do KCL on all nodes not touching voltage sources. Resource. And just make sure you put them in no voltage form. So we're just going to do that. So we're going to basically create an equation for A and an equation for B. Make some sense? All right. So first off is node A. And we're going to take a look at the equations. So we're going to take a look at the situation. So first we have this current going into A. So that's going to be 2. So it'll be positive 2. Then we have, hold on, because I don't want to mess myself up. That's positive 2. Then we have this current right here leaving A. So that's going to be minus because it's leaving. And it starts on VA, ends on VG, which is 0. And you have to divide it by 2. Because remember, current equals V over R. Or technically, it's delta V over R. Whatever. Make some sense? You following me so far?
Yeah. Where did you get VG from? I'm confused. Oh, ground.
Yeah, VG is ground. Okay. And then that's gonna drop to 0. And then next we're gonna do the current leaving the 4. So this one going down. My computer's freaking out, and I'm just gonna keep using the black pen for now because None of the other buttons are working for some reason.
It's simple. It's simple to follow for right now. Problem.
There it is. Everything just went into color. And so from there, you're gonna use the we're gonna go minus, and now we got VA minus VG again, but this time over 4. And then a lot of students will forget that this guy is actually also going into A as well. Because mind you, A is this entire node. A is everything going, A is that whole node. Does that make some sense? So you got to look at all the currents going into and out of that. So we have one final plus. And now this one starts on VB, ends on VA, and is divided by 2. So that's the full equation for node A. Okay. All right, so then node B is going to be very similar. Node B is all of this. So node B, we're gonna do. We're gonna start with this guy, and so that current's leaving. So it'll be minus. And then you do VB minus VA. Note how I put the minus on the outside. A lot of students get mixed up because this will produce a double negative when it goes inside, and so I always leave it. I always write it just like that, so I don't mess myself up. So then we're going to do 2 of these, 2 8s. And so we're going to do minus, and it'd be VB divided by 8. And then another VB divided by 8, because that's both of them. And then finally, you can't forget the current source, which is a value. Remember, this equation that we're writing up is a current equation. This is current. This is sum of currents equals 0. And so you have to include the current source. A lot of students forget to include the current source. And then bam, that's it. So we got 1, 2, 3, 4, and 1, 2, 3, 4. And that corresponds to 1, 2, 3, 4. Yep. And so that's all of our pieces. And so if you want to kind of simplify them and to put it into the form where you can put it into the calculator, you just got to multiply the equations. So I'm going to multiply this top one by 4 to get rid of my fractions. And so I'm going to get 8. And then I'm going to get 2 VA. Then I'm going to get minus VA. Then I'm going to get plus 2 VB minus 2 VA equals 0. That simplifies one more time into 1, 2, 3, 4, 5. So negative 5 VA plus 2 VB equals negative 8. And what I'm going to do is I'm going to just flip the signs so that it's a little bit prettier. Bam. So that's my first equation. Boom. So that's my first equation. Make some sense?
Yes, sir.
Perfect. And you do the same exact thing for the second one. This one I'm just going to multiply by 8 to get rid of the bottom fraction. So I'm going to get a negative 4 VB plus 4 VA. And that's where the double negative came in. Okay. Then I'm going to get minus VB plus 32 equals 0. 8 times 4, 32, yes. All right, and so all I got to do last but not least is to just combine the terms. I got 4VA minus 6VB equals negative 32. And that's my second equation. And that is what you put into your matrix calculator. What this will look like, if you were to write it purely as a matrix, it will look like this. It would be, this is X, this is Y. And so this would be 5, negative 2, 4, negative 6, 8, negative 32. And then it would basically say you could simplify this entire block. I know some calculators do it like that, where it'll say like simplify, and then what it would do is it would break it down. It would produce a new matrix set that would be 1, 1, 0, 0, and then some number here and some number there. And so basically that means that VA would be that number, and then VB would be that number. And that's how some calculators work as well. I'm not sure if that's how Octave does it or not. I'm just kind of throwing out what I know.